record. There you go. All right, so again, looking at our schedule for pre-calc, okay, today, according to the schedule, you are supposed to be at 4.5, which is all about graphs of logarithmic functions. Okay, so we're going to cover graphs of logarithmic functions, applications of logs, and then you will have a test. Okay, you will have a test. But we also have to cover 5.1. So my goal is to get us in class all the way up to this test here, and then to release a video for 5.1 tonight that you can complete after your test. Okay, and again, reminders, if you're not up to this point, it's not the biggest deal in the world, but you have to get caught up here real soon because, as I said earlier, okay, this is your tasks for this weekend. Okay, so not a whole lot, right? Your normal 4 sections. And then all next week, you have to complete your final exams. Okay, you have to complete your final exams. And so what you will have to do, and again, I will post this on Google Classroom come this weekend, all right? But once you finish all of the required assignments, okay, all of the required assignments, okay, once you get to the end point, after you take this test on conics, okay, after you take your conics test, you are going to send me an email, all right? Send me an email or a message on Google Classroom. I don't, however you can get a hold of me. Let me know that you have completed your test, or sorry, that you've completed all assignments. And then I will release to you your final exams. Okay, I will release to you your final exams. And this is going to be a big deal because remember, in order to move up programs, it's not just enough to get a good grade. You also have to have 100% completion of things that I have assigned. Okay, and I have a master list. So what's going to happen is if Quinn sends me an email on Friday night, he says, Miss Judy, I completed all my tests, right? What I'm going to do is I'll go back and I'll look through all of Quinn's assignments, okay? And if he's missing anything, what I'm going to do is to say, okay, Quinn, but you're missing this assignment. So before I can release to your final exam, you have to complete this, right? So then he completes that assignment and then I release to him his final exam. Okay, and this final exam is going to be due, your final exam is going to be due by Friday, next Friday at 11:59 p.m., okay, next Friday, because that's going to give me a weekend to get your final grades, to push those final grades out to you, and then we will start semester 2 come the following Monday, all right? So your goal here is to get everything done and accomplished by Friday of next week. Okay, so again, this is our recommended schedule, but if you're behind, that's fine. You know the tasks that you need to complete. All right, are there any questions at this point here? I'll give you a minute. Are there any questions? Okay, so nothing. Awesome. All right, so moving forward here, again, we have graphs of logarithmic functions, and I am recording this classroom. So again, sorry about the mess up with last time. All right, so I am recording this. So you can go back and watch it if you happen to be a little bit behind here. All right, but we're talking about now graphs of logarithmic functions. Okay, and if we look at the overview here, right, we talked a lot about this earlier, but when I go from X and I put it through some function, okay, I'm going to get out some Y here. But if I do my inverse function, I can get out my X, my original X value, right? We've talked a lot about that, right? So again, if you've added, you subtract. If you squared, you found the square roots, all right? And we can do the same thing here with logarithmic functions, and we're going to look at inverses of logs and understanding the relationship between exponents and logarithms here and how that looks graphically. Okay, so this one only has 6 pages, and it's undoing what you have done is what it starts off with, right? So again, going from I have f, I put it through a function, I come up with y. Okay, I can undo that function by putting it through its inverse here. All right. So we'll watch this video here quickly together here. But now understanding the difference between logs and exponents, and moving forward there. Sorry. Okay, I guess the tree's not talking on this one. All right, so if you have an equation like this one, and you want to solve for x, okay, you need to get x out of the exponent, okay? And we're going to talk about, well, how do I undo an exponential function, right? Okay, so in order to do this, you need to use its inverse, right? You need to use its inverse function. So, oh, apologies. Okay, so there's 3 steps in general to finding an inverse, okay? So the first step there is determining, is the function one-to-one by using our horizontal line test, okay? And if I have a step 0 too, the step 0 would be making sure it's a function, right? So doing the vertical line test, all right? Then you can find the inverse if the function is one-to-one, right? So we're using the horizontal line test to figure out, is it a one-to-one function, okay? And right here, he points out, since one-to-one functions are the only ones that have inverse, okay, the horizontal line test is going to be super, super important, right? And remember, the reason we said that was because when we showed it actually moving, right, we showed the inverses here. If it is not a one-to-one function, right, if it's not a one-to-one function, it's not going to have an inverse that is also a function. Okay, so it has to be a one-to-one function in order to have a function as its inverse. All right, then what we're going to do is we switch x and y. Okay, you switch x and y and we solve for y. So those are our 3 steps here. Again, pretty familiar, and we can do this with all of our different functions. So first off here, using our horizontal line test, it shows that this is a one-to-one function. Okay, then we're going to flip our x and our y value. Okay, and then we're going to then solve for y. So when we solve for y, we get out this new equation, x minus 2 instead of x plus 2. All right, so this is our inverse, and they do it, it's still kind of difficult to see there, but remember, our inverse function is f to the power of -1 of x. F to the power of -1 of x. All right, so that shows that this is f of x, and this is the inverse of the original function. Okay, so another key point here, if 2 functions are inverses, that means that they can undo each other, right? If they're functions, that means that they can undo each other. And I know that it's really simple with that line equation, but where this is going to become important is when we're doing our exponentials and we're trying to figure out those, right? It's really difficult for us to be able to understand that right off the bat. Okay, so again, what it's saying is you can undo. So if x goes to something, right, we can put it through its inverse, and then you'll get out the value. Okay, so, right, if you put them together, it should undo. It's very convenient, right, and it's really nice about functions. Okay, so the same thing happens if you put them in the reverse order. Okay, the same thing happens if you put them in the reverse order, right? So if I subtracted 2 first, then added 2, it doesn't really matter, right? So knowing a function and knowing that function's inverse is going to help you go between those 2 different types of functions. So then the next question is, okay, if this is the inverse function for basic equations like a linear line, okay, how can we use this moving forward? All right, so if we're looking at exponential functions, if we look at exponential functions, the question is how do we move between, how do we move between exponential functions, right? How do I get that x out of the exponent? And maybe you figured it out, but there is a relationship between exponentials and logarithms. Okay, so, All right, looking at another example here, using the horizontal line test, it shows that this function is 1-to-1. Great, we switch x and y, and then we solve for y here. So the inverse function of this is the cubed root of x. So again, understanding that inverse functions are inverses of each other, they can undo those relationships. So for example, if I take x, I take the cube root of it, and then I cube it, I'll get x back out. Or if I take x, make that x squared, or sorry, make that x cubed, then I take the cube root, it's going to give me the same thing. All right. So again, to write what this notation is, this is saying I have my inverse of, instead of x, I write my f of x. Right. So again, instead of writing the cube root of x, I've replaced x with my x cubed. All right, again, that's just reading the notation there, knowing where to plug things in. And I can do the same thing. I could write f of f to the negative 1 of x, or inverse f of x, equals, and this would give me my parentheses with my cubed root of x, and then that whole quantity would get cubed. Right, so there's what I was talking about, right? If I wanted to put the inverse function inside of f of x, right, I replace x from my original x cubed, and I put that as the cubed root of x, that quantity gets cubed. So we're going to look at the same thing for inverses here. So if I have 2 to the power of x, okay, it is a 1-to-1 function, so we can do this process. Now we switch x and y. So then the question becomes, how do I solve for y there? All right, how do I solve for y? And we just should have learned, right? We learned those in the video, so hopefully you watched them. There is that relationship between exponents and logs, right? So if I have x equals 2 to the power of y, okay, it's like saying y equals log 2 of x. Log 2 of x. Okay, and the reason this is because as we read this, or as it showed you yesterday, when you see log 2 of x equals question mark, what that's saying is 2 raised to the power of what? 2 raised to the power of what is going to give me x, right? And we worked a lot with this yesterday. But you could have said log 2, it could have been log 2 4 equals question mark, right? So that would be log of 2 raised to the power of what is going to give me 4, right? And my answer would have been 2 there, right? Because 2 raised to the power of 2 equals 4. And what I do sometimes to make sure that I'm keeping this straight is, again, have those study sheets, or have your little note sheet where you have this notation written down somewhere, right? You have those general forms written down, because it's really easy to get a little bit confused, and that throws everything off there. But again, to read this, it's saying log base 2 of x is equal to y. And what that means is what value of 2 2 raised to the power of what value is going to give me x, right? That's how we ask this question here. All right, so we find out that logs are the inverses of exponentials, and exponentials are the inverses of logs, right? And this is true for other base values here. So f of x equals x to the power of 5, right? The inverse of that is log 5 of x. Log 5 of x. Okay, so there's 2 that we're going to use a lot here. Oh, sorry. All right, there's 2 that we're going to use a lot here. I keep passing it up. Sorry. We're going to use base 10 and base e, right? So again, remember that when we have base 10, that's the log that you're going to have on your calculator. So where it says log, that's going to be log base 10, right? And if you don't see the base, it's automatically assumed it's log base 10, all right? If you have log base e, that's that ln button. That's that ln button, okay? So that's the natural log. All right. So when you see a logarithm with no apparent base, right, it's considered log base 10. So right here, this is log base 10 of x, right? That's saying, again, 10 raised to the power of x equals our y here. All right. This can undo. Same thing here. E to the power of x, well, that's just saying ln of x. That would be log, because log base e is ln. All right. All right, and yes, E is a value, a constant value. You do have the ability to type in E on your calculator. All right, so that is the button that is above your LN button. Okay, so if you look on your calculator, on the left-hand side, you have your calculator, right? The third button up from the bottom should say LN, and then in a color above it, mine's colored blue, it says E to the power of X. Right, so if you plug in E to the power of 1, you're going to get out this 2.7182 value. All right, so again, understanding that logs and exponents are inverses of each other is going to be really helpful, because again, we can then move now between different functions. We can move between those two functions. All right, so using the inverse relationships here, okay? Log base 10 of 5. Log base 10 of 5. All right. You can then solve these without using your calculator. Right? You can solve these without using your calculator. So for the sake of time here, oh gosh, for the sake of time here, I'm gonna let you guys try these on your own, because you can actually type these answers in. All right, and if you just type in random values, right, it's going to tell you which ones are incorrect, right? And if I type in, again, still random values, there we go, submit. And of course, mine's not letting me do it. All right, but once you get through your other two attempts, okay, it will give you the answers when you're done. So if you're stuck on this one here, you can go through and look at this and look at your answers there. All right. Now, inverse by folding. Okay, inverse by folding. Again, that's talking about folding your graph here. And it's saying here you can exploit the fact that the X and the Y variables switch roles to make an easy sketch, right? Again, sketching means it's not perfect, but we can draw a relative relationship. So let's take a look here.
You've seen how functions that are the inverse of each other are related by their equations. Now you will see how their graphs are related. As you've seen before, the graph of this function looks like a diagonal line passing through y equals 2. The inverse function that you found can also be graphed. If you look closely, you'll notice there is a line of symmetry that passes through the origin. This line of symmetry follows the line y equals x. Take a look at another pair of inverse functions. Using the same line of symmetry, you can find a second function line. Imagine this by mentally folding the graph along the line of symmetry. The new curve you get is the inverse function. This same symmetry.
Oh, right. Sorry. Pause. Again, remember, it's
inverse function.
Reflecting across that middle line there. Okay, so again, it's not across the X or the Y, it's across this Y equals X line. Okay, so again, it's the way that I do this here is I draw my original function, and then I draw, again, a rough estimate of my Y equals X line, And then what I try to do is just try to mimic the shape going the opposite direction, okay? So if you're just asked to sketch a general shape, as long as it looks relatively like it's supposed to, it's gonna be fine here.
This same symmetry is seen in exponential functions with their inverses, logarithmic functions. If you plot the function 10 to the x power and then fold along the axis of symmetry, you get the graph for its inverse, log x.
Okay, again, perfect. As long as you can see here the general shape of what this should look like, there's relative spacing, right? And if you would feel more comfortable, you can pick a couple points here. Like obviously we talked about how this graph's gonna go through the point 0, 1, right? So that means that you should have a point that goes through 1, 0, okay? So a couple easy points and pointers like that.
Here's just the logarithmic function. Do you remember that the exponential function grows really quickly?
Yes.
The logarithmic function, by contrast, grows very slowly. The function only exists for values of x greater than 0. You can see that there is a vertical asymptote at x equals 0. You can also see that y takes on values that include all real numbers. Finally,
okay, so let's unpack that for a second. There was a lot in there. Okay, so there is an asymptote, which means a line that will never get crossed, or it approaches rapidly, maybe crosses in the horizontal, but vertical ones we don't cross. So there's a line here, and you can tell because it looks like the graph gets really close, but it never passes. So that's your vertical asymptote. All right, so our domain here is 0. Let me back this up here. Is 0.
You can see
curses.
Values of x.
All right, it's 0 to infinity. All right, infinity because it's going to keep going forever and ever and ever on the right direction, but 0 because it's never going to cross that vertical asymptote. And again, highlighting that 0 is in parentheses. It's not inside that bracket. So it's in parentheses. That means it's not included. It's not included.
Greater than 0. You can see that there is a vertical asymptote at x equals 0. You can also see that.
All right, and then finally that range there. So that's our list of values for y. Okay, our list of values for y. So we can go forever and ever and ever in the negative direction, and this will keep going forever and ever and ever in the positive. So that's negative infinity to positive infinity, right? And what you should have noticed there is the domain and range, those values flipped when we took the inverse of our equations, right? So normally if we had our exponential, our domain would be negative infinity to positive infinity, and our range would be the opposite, right? That's 0 to infinity.
Y takes on values that include all real numbers. Finally, you can see that the logarithmic functions crosses the x-axis at x equals 1. For all logarithmic functions, the log of 1 is always 0.
Okay. All right, so that's talking about, again, folding across that line y equals x, right? So then moving forward here, following the logarithms, okay, we can now understand how to plot logarithms. We can understand how to take the inverses and how to work back and forth to solve problems. Okay, so looking here, we have 2,500. Oh, gosh almighty. 2,500 is equal to 5e to the 3x power. All right, again, we can immediately look here and say, okay, well, 3x. All right, in order to undo that exponent, I have to then use logs, right? So I have to use logs. So what we're going to do is we're going to change this equation here. But before we can do that, we had that 5, right? We had that variable 5. So when we were originally talking about changing these functions, right? Changing these functions, we didn't have multiple parameters, right? And something that I want to point back out here, if we're dealing with e to the power of something, right? That should trigger in your head when we do logs, we have to do the natural log, right? We have to do that ln. All right. If this was just 5 to the power of 3x, right? 5 to the power of 3x, there wasn't this e here. Okay, we would be doing a log base 5, and we wouldn't have to do this original division. But again, the fact that we have e here is changing things. Okay, so we have to first divide by that 5. All right. Then we have to take the inverse, right? So we're taking the inverse, which means we're taking the natural log of both sides, okay? And again, we have to take both sides because we can't just affect one side of the equation. Okay, so this is the final stage here. So we can't just take one side. We have to do ln of both sides. All right. So when we take ln of both sides, all right, again, this is like saying log of e, log base e of 3x. All right. So what then, moving forward, okay, since we had log ln of e, okay, ln of e, or log base e of e, right, that equals 1. Log base e of e equals 1. So let me write that out for you. All right, what it looked like, it said log, let me make this a color that is a little bit brighter to see. There you go. All right, so log of e is equal to, and I'm sorry, I can't get this to be a lowercase or that subscript. So apologies. I'm going to write log of e like that. Okay, this is like saying ln. So when it said ln of e to the power of 3x, okay, what this was saying was log base e of e to the power of 3x. All right, that's what that guy was saying. Log base e of e to the power of 3x. All right, well, if we just look here at log base e of e, all right, what value, if I have e to the power of what value is going to get me out e? Well, that should be immediately, oh, sorry, log base e of e gets me what value? Again, that's like saying e to the power of y is going to get me e. All right, well, this obviously is y equals 1. Y equals 1. So what this is saying here is if I have log base e of e, this value is 1. So this equation we have right here, it won't let me do multiple colors, curses. All right, sorry. Well, this value right here turns into 1, or sorry, this value turns into, these guys will cancel each other out. Okay, these guys will cancel each other out. All right, but as we talked about earlier, if we have something, right, if I back that guy up, right, if we have something raised to the something power, before we start playing with it, we bring that 3x out, right? So we bring that exponent out in front. So this becomes 3x log to the e times by e, or log base e of e. All right, so again, this then turns into 3x times by 1. That turns into 3x times by 1. All right, so again, a lot of steps there, so let me explain it a little bit. All right. Okay, so again, walking back through this, I can't, there we go. All right, so if we start with our original equation, okay, we start with our original 2500 equals 5e to the 3x, okay? We cannot have some number and e, so we get rid of that 5 by dividing to the other side. All right, then what we do here, we have e to the power of 3x. So we have to have an expression that undoes e, right? That undoes e. And what we found out is that the process that undoes e is the natural log. The natural log. And the reason that is because the natural log, if we're looking over here, the natural log of e is equal to ln. The natural log of e is equal to ln. So when I write natural log e of e, that's like saying e to the power of what gives me e? And that's going to be 1. All right? So what we do is, we know that that's going to cancel each other out, so we have to multiply both sides of the function by ln. All right? We can't just focus on one side, we have to do both. All right, so we multiply both sides of the function by ln. right? And again, if this is a log and it's raised to a power, what we have to do is we have to pull that out in front. We pull that out in front. So again, this becomes 3x ln of e. All right, this becomes that 3x ln of e. All right, and as we found out, ln of e, or log base e of e, that's just equal to 1. So this is like saying 3x times by 1. All right, so that's like saying 3x times by 1. All right, now, if we go to the next step here, you're going to find out that that cancels. So we're left with ln of 500 is equal to 3x. ln of 500 is equal to 3x. So then what we can do is we can divide both sides by 3, and we get x is equal to ln of 500 divided by 3. And you can 1,000% plug that into your calculator. Again, you just plug in ln, right? So your ln function, 500 divided by 3. That should give us 2.07. Right? We plug that into our calculator, we're going to get like 2.07. And I'm not sure if we've seen this before in this class, or if you've ever seen this, but these squiggly lines, okay, means approximately equal to. All right? So if it's a straight line, it means it's absolutely equal to, right? The equal signs we're used to, absolutely equal to. If it's a squiggly line, it means it's approximately equal to. All right? Looking at another example here, okay? Now we have 2,000 equals 2 to the power of, I know it's difficult to see, but there's a decimal point there. So that's 0.04 to the multiplied by x. Okay, 0.04 multiplied by x. So for this one here, what we're going to have to do is we could either do the rule of logs. Okay, we can do the rule of logs here. All right, but as this is saying, we could either do, since this one is got the exponent on a value of 2. Okay, so I'll back it up here. All right, this is a value of 2. All right, and the only 2 things we have in our calculators, or the ones that we're going to use most familiarly, is either ln, which is log base e, or our log function, which is log base 10. All right, since this is neither of these, okay, you can either use log or ln, right? You get to choose which one you want to use. All right, they're using ln. Okay, so you multiply both sides by ln. Okay, but what we can notice here now is, remember our rule, if we have ln or log of something raised to the power, that power comes out in front. So what this is going to turn into is 0.04 x times by ln of 2. So that's what that's going to turn into. Give it a second here. Perfect. 0.04x times ln of 2. All right. Or again, you could have done this with logs. Same thing, as long as it's the same base, right? Either base e or base 10. Okay. So now what we can do is we can divide both sides by ln of 2. All right. We can divide both sides by ln of 2. All right. And, oh, they jumped this step there. All right. Once you divide by ln of 2, you would get ln of 2,000 is equal to 0.04 times by x. So then eventually you're going to also divide by 0.04. They just combined it all in one step here. All right. So now remember, ln of some number is actually going to give you a number in your calculator. So you can plug this straight in and use it as is. You can plug this straight into your calculator and use this as is. All right, and squiggly line means approximately equal to. All right, so here's a list, right? And this will be on your study sheet here. But if the function is the inverse of b of x, you can use it to solve for x, right? You can use it to solve for x. And this is some of the stuff we've summarized for our graphs here. Apologies, I thought they were summarizing the steps. That's got to be later on. Okay, but again, remember, it's understanding the forward and reverse direction and just using math to get out the values that you want. All right, so if we look here at the study sheet, oh gosh, I keep doing that today. If we look here at the study sheet, the 3 steps for finding the inverse, okay? If the inverse is 1-to-1, great. You can do this, right? But you've got to use the horizontal line test to figure out if it's going to be a function, okay? Then you switch your x and your y's and you solve for y. All right, so again, you guys should be able to do the inverse of some basic functions here, all right? And basically the rule of that is if they're inverses, they can undo one another. They can undo one another. So for example here, where this is going to be useful for us is when we're talking about logs here. So y equals 7 to the power of x, okay? Well, exponents, their inverses are logs. So this function turns into y equals log base 7 of x, okay? Because how you read this is 7 raised to the power of y, or sorry, 7 raised to the power of x is going to give me y. 7 raised to the power of x is going to give me y. All right. So then the inverse function of 10 to the power of x, okay, that is log of x, right? And again, it's not shown here, but this is when you don't have a base, that's log base 10. That's log base 10 of x. All right. While the inverse for e to the power of x is ln, because ln stands for log base e of x. That stands for log base e of x. All right. So for these guys, this is a really good example of how these cancel out, right? So I have log base 10. I have log base 10 to the power of log base 10 of 10 to the 12th, right? So log base 10 and the 10 are going to cancel out. So you have just left with 12, right? And again, if I were to show you all of the steps for how this works here, okay, this function is log base 10 of 10 to the power of 12, okay? So that turns into 12 times by, and I'm going to get rid of the log base 10, but you've got log base 10 of 10. All right? And since log base 10 of 10 is 1, it's like saying 12 times by 1. So that's how I get out my value of 12. All right? Same thing here. Log base 10 of 10 raised to the power of 9k. You bring that 9k out in front, log base 10 of 10 cancels. All right, same thing here. ln is log base e. So this is saying log base e of e to the power of 40. You bring that 40 out in front, log base e cancels with e. So you're left with just 40. All right. Log base e by itself, right? This is going to be equal to 1. Same thing as if you just said log of 10. That would be equal to 1. All right. And then working in the opposite direction here. Log of 4 of 416, right? That's still, bring that 16 out in front. Log of 4 cancels out. If I have e to the power of ln of 6x, okay? E and ln are going to cancel out. E and ln are going to cancel out. So I'm left with just 6x. Okay. So again, where that gets really, really important is down here for page 5. Okay, I would suggest trying these out here, but we can walk through the steps together. So, all right, I have 3e to the 5x. All right, well, I know I have to get rid of this 3, so I've got to carry it over to the other side. So I'm left with 2,000 equals e to the 5x. All right, now the function that will undo e is going to be ln. All right, it's going to be ln, and I don't like that they keep skipping this step, so I apologize here. All right, but I have ln on both sides. So I have ln of e to the 5x. Okay, 5x again gets carried out in front, so you have 5x times ln of e. All right, ln of e is equal to 1, so it's just like saying 5x. Right, so then you can either you can calculate out the value for ln of 2,000, and then divide 5 by both sides, or when I get to this stage, I would have it set as ln of 2,000 divided by 5 equals x. All right, you should still get out around the same value. All right, now if we look at b here though, its base is not something that we easily know. It's not a base 10 and it's not a base e. So for this one, we can't cancel out our ln. And our base value. Okay, so we multiply both sides either by log or by ln. It doesn't matter, whatever you want. Okay, as long as they're the same in this case. So they picked ln. All right, so you multiply both sides by ln. You bring down this exponent, right? That gets carried out in front. So they show it there, 0.1x times by ln of 8. All right, you divide both sides by ln of 8 because we're trying to get x by itself. So I've got ln of 7,500 over ln of 8. Then what you're going to do is divide both sides by this 0.1. And you're going to get x by itself. And then when you plug in ln of 7,500 divided by ln of 8 times by this number here in the denominator, you're going to get out about 42.92. And again, remembering, squiggly lines equal approximately. Okay, equal approximately. Looking at this checkup here, okay, I would really, really suggest at least being able to know what the equivalents are equal to. All right, knowing what the equivalents are equal to. All right, that's saying if I went in the reverse direction, right? Understanding, yes, it is important to understand the domain and range, so please make sure you can do those as well. And what that is again, it's modifying the original equation. So remember, if we know what the log equation looks like, right, we knew that it was going to be a reflection of our exponential across that y equals x. So if I draw my y equals x line, okay, so my original exponential function crosses through that point 0, 1. Okay, passes through that point 0, 1. So we know that our log, okay, our log is going to look something like, again, crossing through that 0, 1. Sorry, I'm not the best artist here. It's going to look something like this. Okay. And then what you can see here is, right, it's going to follow the same pattern that every other translation did. Okay, it moved up 2 functions. So it moved, instead of going through 1, 0, it's gone up 2. So 1, 2, and it's gone to the left 3. 1, 2, 3. Okay, so it's that normal translation. And again, sorry. The graph that they drew, sorry, I wasn't bouncing the correct numbers, right? So 3 over, all right? And again, I apologize, my drawings are not always the most accurate here, all right? But says, and that's what it's meaning when it's saying use what you know about horizontal and vertical shifts. So we know that this +2 means we had to go up 2. This +3 inside the x value means we had to go left 3. All right. Okay, so that is, in general, that is your checkup here. And, all right, and then the problems that we already did and worked through a couple, but just a lot more practice here. So please make sure if you feel uncomfortable with this, try it out and look at the answers that they give you on this checkup. Okay, they do a lot where they really walk through and they show you those steps there. All right, so again, it's all about making sure you know what the inverses are. All right. Again, more graphs here, but if this is your original function, g of x is your inverse function. All right, and again, knowing that it crosses that middle line of y equals x. Okay, it crosses that middle line of y equals x. All right, so that rounds out this first unit here. All right, that rounds out 4.5. All right, so you do have a quiz on 4.5 here. All right, and we have 4.6 is the last lesson we're going to cover in class today. So 4.6 is the last thing we're going to cover. All right, 4.7 is just your wrap up, okay? So 4.7 here is what you need to do for your test here, but I'll mention that when we get there. All right, so looking at the application of logs. All right, where do we actually see this here? All right, I talked a lot about how exponentials are used for interest, right? And now we're going to figure out how logs are used, right? And sometimes it's also called exponential decay function, right? It's called the exponential decay function. So let's look at here on cooling coffee.
Take a look at a graph that describes what happens to the temperature of the coffee. Let the vertical axis represent temperature and the horizontal axis represent time. Start by marking the temperature of the coffee when it is first poured. Since the coffee will not get cooler than room temperature, draw a dotted line to indicate where the temperature will level off. Finally, here is the curve that shows the temperature dropping and leveling off as it approaches room temperature.
Okay, so that would be a good example of how we could use this exponential decay function, right? It's not going to get colder than room temperature. It doesn't make sense, right? So it can't get any colder than room temperature. All right. We'll look at some more examples here. All right, so this is called Newton's law of cooling, right? And this allows you to determine the exact temperature of an object at any time, as long as you know the start and ending temperature and this thing called the cooling factor. All right, and no, you won't have to memorize a cooling factor or something like that, right? But this could be a really good example of a problem we give you in a science class, right? So you guys are going to be taking physics next year. So this would be a really good application of math in physics, right? So instead of doing it with liquids, right, we could do this with metal, right? And we could say something along the lines of, hey, you're an engineer and you've got people making parts for you on site, okay? Your parts need to be room temperature before you can assemble them. How long after making the parts do you have to wait before you can start assembling them, right? Knowing that metal melts at X temperature and it is 75 degrees outside, right? So that would be an example of a problem that you could use, again, use mathematics for, but now you're getting this application piece. So if we look here at Newton's specific law, what the equation is.
Sir Isaac Newton developed a mathematical model called Newton's law of cooling that may be used to calculate how long it will take the coffee to get to a drinkable temperature. What do all those letters stand for? It looks complicated, but it really is not. Here's what they all mean. T of T is the temperature in degrees Fahrenheit of an object at a given time T. T sub A is the temperature of the surrounding or ambient environment. T sub 0 is the initial temperature of the object. K is a positive constant. How do you use Newton's law of cooling? Let's look at a specific example. Suppose you pour a cup of coffee that is 200 degrees Fahrenheit and leave it on the table in a room that is 68 degrees Fahrenheit. 10 minutes later, the coffee is 150 degrees. How long before the coffee will be 100 degrees Fahrenheit? Start with Newton's law of cooling and then write down the values you have been given. You want to know what value of T will make T equal.
Okay, so again, this is a classic example of you're given an equation, you're given all the values you need, but you have to figure out what do you have and what do you need to solve for, right? So for example, you're given T0, that's the initial temperature of the coffee, or the tea, sorry. Okay, you're given TA, that's your room temperature. Okay, that's your ending temperature. And you know that T at time 10 equals 150. So you can solve for the other constants that you might be missing. So those values up there, that negative KT, right? You can solve for that and then have an expression to figure out the temperature at any time.
100. In order to answer this question, you first have to find the value of K. In order to calculate K, fill in all the other known values. Simplify, then solve for K by using the
Okay, pause, right? So then once we've simplified, we're at this point here, and he's going to explain it again, but I want to highlight, right? You're going to try to take the inverse of this relationship, and we should know by now the inverse of e to an exponent is ln, right? We can take the inverse of e by doing this ln function. So when we do this ln function, we're going to drop down our exponent, so then we can solve and make it easier.
Log function. Now that you know K, put that into Newton's law of cooling. Then, since you want to know what it is when T is 100, substitute 100 for T and solve for T. Approximately 30 minutes after the coffee is poured, it will be 100 degrees Fahrenheit. Newton's law can be used for more than coffee temperatures. Did you ever wonder how those detectives on CSI figure out time of death? One method has to do with the temperature of the body. Experimental data shows that after death, the body will cool from its normal temperature of 98.6 degrees Fahrenheit, according to Newton's law of cooling, with K equals 0.1947, and time measured in hours. Suppose the temperature of a body found outside is 70 degrees Fahrenheit. If the outside temperature is 55 degrees Fahrenheit, how long ago was the time of death? Newton's law of cooling tells you the answer. The time of death would have been about 5.5 hours prior to the discovery of the body.
Oh, right. So again, I know it's kind of maybe potentially morbid there, but that's how we can figure out how long ago somebody died, right? So again, this is a really, really good practical application of mathematics outside of roller coasters and outside of trying to fit Rice Krispie treats, right? So there's a lot of different applications, but you have to kind of think outside of the box when getting to those. All right. But before we go on to that, again, the main thing that I tried to harp on in my classes is understanding what equation you have, what variables do you already have the information of, right? So taking inventory of what do you have, what don't you have, like what are you looking for, and then you plug in and try to solve from there, right? Again, to me, it's kind of the same process every single time, but the variables are going to change, what you're solving for is going to change, but it should still be a pretty consistent process every time. Okay, and you guys should have talked about this. I know for a fact we did in all chemistry classes, radioactive dating, right? That was talking about nuclear dating, all right? And this has to do with nuclear components, right? So we talked about half-lives, right? Half-lives of nuclear substances or nuclear radioactive compounds, right? So those nuclear radioactive compounds, right? Those really heavy ones. We talked about uranium and all of that stuff, okay? So we can talk about this thing called half-life, right? And that's a way of we doing radioactive dating. So I know they'll talk about it here, but that's how we can figure out how old dinosaur bones are or how long ago somebody or something existed, right? So we can do this radioactive dating by, again, applying a mathematical model to the information that we have.
Archaeologists use mathematics for another kind of detective work, determining the age of an artifact. Carbon-14 is a radioactive substance found in living organisms that decay after the organism dies. The half-life of carbon-14 is 5,730 years, so you can write an equation that represents the amount of carbon-14 present T years after the organism dies. Suppose an artifact contained 63% of the amount of carbon-14 it contained originally. How old is the artifact? If you divide both sides of the equation by C sub 0, you are left with this equation. Now solve for T. We conclude that the artifact is approximately 3,819 years old.
Okay, so again, another really good application of math that where it's kind of hard to see at first, but once you understand what we're looking for, right, the math just jumps out at you. All right, another one here, exploring logistic growth. All right, logistic growth. We have to talk about that, and to give you the definition, it's an exponential function that starts out growing exponentially and then slows as it approaches the horizontal asymptote. All right, this is also called carrying capacity. All right, and a really good example of this is in biology, when you were freshmen, you talked about how many animals can fit in a certain ecosystem, right? So that would be the carrying capacity of those animals, right? So again, to give you a situation, right? Maybe you're on a desert island, and that's exactly what it's going to give you. You're on a desert island, right? If you can only sustain about, let's say, 1,000 snakes, any more than 1,000 snakes, we don't have enough food. Any less than 1,000 snakes, they can then start to populate. So it's going to ride around, right? 1,000 snakes would be an example of carrying capacity. All right, so if we continue to look, though, at their example here.
Newton's law of cooling and carbon-14 dating are examples of exponential decay. Exponential functions are also used to model growth for such things as savings accounts and population. When an exponential function is used to describe population growth, the underlying assumption is that the population will continue to grow without bound. But what about situations where some other factor, such as limited food and water, keeps the population from growing without bound? These situations are best described by a logistic growth curve. The graph of a logistic growth curve looks like this. You can see that in this section, the graph looks like an exponential growth curve. But in this part, the graph changes. The rate of growth slows, the graph levels out, and approaches the horizontal asymptote, y equals L. The function that produces a logistic growth curve looks like this. As you can see, L indicates the upper limit for the population. L is sometimes referred to as the carrying capacity. How do you think the value of B will affect this function? You can compare the two functions shown here by graphing them. Notice that the only difference between ft and gt is the value of B. The larger B is, the faster the function reaches its carrying capacity.
Right, and you can think about that as how many things double, right? So for example, if this is 2 here, that would say for every individual they have 2 offspring, versus down here for every individual they have 8 offspring, right? So that would be an example of differences. Okay, maybe one more example here. Nah, we'll skip it. I'll let you guys do this one here if you want. You can calculate the carrying capacity of rabbits.
This question is really asked.
Okay, you can calculate the carrying capacity of rabbits, looking at how many rabbits were initially introduced, right? So how many rabbits did you start with? Okay.
To answer this question.
And then when the population, figuring out when the population will reach a certain number, right? That number you can effectively ask as if it's the carrying capacity. All right. So looking at our study sheet here, okay, looking at our study sheet, in an exponential decay function, the value of the function decreases according to the exponent, which is negative. All right, so again, think decay means go down. All right, decay means go down. If it's a growth, it's going to go up. All right, Newton's law of cooling, there's the equation for it. Okay, you're probably going to need that for your quiz, so make sure you have that handy. Where you have different variables and they stand for different things. Okay, so then based on using this equation and understanding what those variables stand for, you have a worked problem here. Okay, so you're going to pull out what you have, you're going to take your inventory, you're going to plug it into your equation, see what you're missing, and then solve for your variable there. Okay, again, we talked about carbon-14 dating. All right, so again, the equation for that guy is right there. And again, it's talking about dating back for how long things have been gone. So again, you're pulling out what you have, taking inventory, plugging it into the equation, and solving for your missing variables. All right, the thing I do want to point out here, it says, suppose the artifact contains 20%. All right, and again, remember, we write 20% as 0.2. Okay, we write it as 0.2. We don't ever write it as 20 because that would mean a lot different. I mean 2,000%. Okay, logarithmic growth curve. Okay, so a logarithmic growth curve for things like population is this guy. All right, again, upper limit is the carrying capacity. All right, the upper limit is the carrying capacity. Draw the general shape of a logistic curve. Again, it's going to be something like this. Something like this. All right, and if it's specifically a one for the carrying capacity, okay, you have this value L. If you were looking specifically for a carrying capacity, it would go and decay at that L value. All right. So then again, here's more worked problems based on squirrels. All right. So that brings us to the end of Unit 4 here. All right. So we're not going to go exactly to 11:30. We'll end this a little bit sooner. But what I want to point out here is you have really good reviews. Okay, so this first one here, if I can kind of fly through it to remind you, okay, we introduced ourselves to exponential and logarithmic functions. Okay, so hopefully you guys can do this and go through. This is just a vocabulary review. All right, so if these click and drags aren't working for you, as long as you can go back to the different sections and look at the vocabulary, you're gonna be fine here. All right. These are all the computational rules for exponents and for logarithms, okay? You have these in your study sheets, but they're gonna be super, super handy, all right? And again, notice there are some similarities here, okay? There are some similarities, and again, these processes undo each other, right? These processes can undo each other. But if I have two things and I'm multiplying, I add them. Right? If I have two things and I'm multiplying and I'm adding them. So kind of the same here. These guys are multiplied together, so I'm going to add them. These guys are divided, so I'm going to subtract. All right, this one is raised to the power of, so I'm going to multiply. This one is raised to the power of, so I bring P out, it's going to be multiplied. All right, so knowing all of that stuff. And then knowing that there was a couple computational rules, like if you had log of A of n and log of A of b, you cannot just combine this to say log of A of n over b, right? That forms something totally different, right? So you gotta know that. And here in this example, log of A, as long as A is the same value, it doesn't matter. Right, so the ones that we're going to use mostly is either going to be log base 10, which is just log, or we're going to use log base E, which is ln. All right, reminding you of geometric sequences. Okay, so you have explicit, you have recursive, and then you have the ability to sum up a partial ratio. Okay, so again, focusing on understanding what the ratio is and then being able to sum up the different parts. Again, the hardest thing I think personally is making sure you understand what are all those variables mean and how to pull them out of your different equations. All right, looking at our graphs here, we have exponential decay, we have exponential growth. All right, understanding that A here has to be between 0 and 1, and then A has to be 1 here for a growth. Okay, that's going to be one of the main points there. And knowing that regardless, it still passes through the point 0, 1, 0, 1. And they are coming really, really close, but never going to touch the y equals 0 line. All right. For logarithmic, okay, for logarithmic, it is, again, a reflection or else across that y equals x line. What it's going to look like is it's going to get really, really close to 0 here. It's going to keep going positively, and again, it's going to cross that point 1, 0. Okay, so then for radicals, all right, I know it kind of looks similar here, but the logarithmic function starts lower than the radical, right? Radical starts there at 0. Okay, so radical starts at 0 and goes upward, and the difference here being that 0 is included. So look, it's in that bracket. 0 is included. Okay, and when this is a, when n is a even number, the graph is going to look like this. When n is an odd number, it's going to have that S shape. Okay, kind of similar to when we had our exponents of in algebra 2 today, when it was x squared or x to the 4th, it was that U shape, and when it was a cubed, it had that S shape. All right. And then understanding transformations. So again, it is the same rules that we've been doing. So I'll let you try this on your own. But remember, we have stretching and compressing. We have moving left, right, up, down. Okay, and we have reflecting across the different axes. Okay, so there's a lot of those that you can do. And again, it's all about picking up on general trends here. And then obviously we had a lot of applications. I think now when we get into math at this higher level, that you can see a lot of obvious applications, or sorry, maybe not so obvious, but once you understand what we're talking about, they become a little bit more obvious. So some of the ones we talked about was interest, right? Like compounding interest, how to make your money work for you, and how credit card companies are taking a lot of money from us, right? Compound interest. All right, then we have carbon-14 dating. Okay, so that's one we just got introduced to. And again, this is the one to figure out how old something is. All right, other ones that we're introduced to was Newton's law of cooling. So figuring out the temperature of anything based on the room temperature there. Then we had logarithmic growth, right? Logarithmic growth. So carrying capacity of animals in a certain environment. Okay, that's the one that I mostly think of here for logarithmic growth. Or sorry, logistic growth. All right. And then finally here for 4.7, just a lot of calculator review. All right. Again, please make sure you read it. I know it's kind of tedious here, but it's going to be really, really helpful for you. If you have any questions with calculators, again, like I said, I have an 83 and 84, and I have that Inspire digital one, so I can definitely help you through this. But again, playing around with the different buttons, and they're going to talk you through this here, but the buttons that I want to highlight to you that we specifically talked about was the Y equals button, right? That's how you make your graph in the upper left-hand corner. If you look at that trace button, okay, that trace button lets you walk across your graph. Then if you hit second trace, you can calculate things like x-axes and y-axes and intercepts and all of that stuff. And then the other ones we talked about was remembering that little up arrow means superscript, right? So that's your exponent button. And then you have your log and ln buttons on the left-hand side, okay? Your log and your ln buttons are on your left-hand side. So those are going to be the ones that are most important for us here, all right? If you want to do the practice or the discussion, those are both extra credit for you. Those are both extra credit, okay? You will have to do this computer scored test, all right? So that's your CST. And then later on this afternoon, I will release to you your video recording for 5.1, okay? So that will be what you have to get through. And again, and if you're confused, you just go back here, look at your pre-calc schedule, all right? So we got through in class, we got all the way up to your test here. So you're going to take this test along with these two quizzes for your homework tonight. I will release a video for 5.1 later on. All right. And then again, additionally, this weekend, I will post those videos tomorrow. You can work at them at your leisure. All right. Once you have finished and you've gotten all the way through your conics section and you've done all other things that are required of you, you will send me an email saying, Miss Judy, I'm done with everything. I'm going to double check to make sure that you're done with everything. And then I will release to you your final exam, which you have all of next week to work on. You have all of next week to work on. Okay. Are there any